We are now going to talk about binary space partitioning trees as our final ray tracing acceleration structure. This gets to the concept of spatial subdivision, which is a different idea where we subdivide space rather than objects. In the bounding volume hierarchy that you just saw, each object is in one of two sibling nodes. A point in space may actually be inside both nodes because the bounding boxes can overlap. In spatial subdivision, each space point is in exactly one node. You're subdividing space, but the object itself may lie in multiple spatial nodes. You've already seen an example of this in terms of the uniform grid, where the challenge was keeping all of the objects within a single grid cell and in being able to traverse the grid properly. For binary space partitioning or BSP trees, they have been used for visibility and ray tracing. We can consider both axis-aligned splits and non-axis-aligned splits. If the splits are axis-aligned, which is very common in today's ray tracing software, then it is called a KD tree for axis-aligned. You want to be able to split space or you want to binary space partition along the planes. Once you have developed this binary space partitioning representation, you can enable fast queries and a simple back-to-front painter's algorithm traversal. The construction of the binary space partitioning tree is conceptually simple. You select a plane as the root of the subtree. You split into two children along this route. You can choose a random polygon for the splitting plane, and you need to split the polygons that intersect this plane. I do also want to acknowledge that many of my binary space partitioning slides are courtesy of my former colleague, Professor James O'Brien. Here is the initial state of the BSP tree. You can see that I have 7 objects, A, B, C, D, E, F, G. What I'm now going to do is choose an object A at which to split my BSP tree. And I split it into the left and the right components. D and B form clearly into the left component. E, F, and G clearly land in the right component. For the object C itself, I need to split it into 2 parts, which is C1 on the left and C2 on the right. And so I will need to split objects corresponding to splitting plane. I can then consider a split by B on the left, which will put C1 and D in different parts. And similarly, I can go through, I can split along C2, and now I would have these splits for F and G. E will need to be resplit, and so on until I get to the individual components. Notice that we have now added the signs plus and minus to these splits. That will help us in traversing the tree. So let's talk about the BSP tree. We continue splitting until we reach the leaf nodes. And the visibility traversal follows this order. You do child 1, which is child 1 depends on where your viewing direction is. We'll get to it in a moment. Then you do the root, and then you do child 2. You are guaranteeing that you will always intersect geometry in child 1 before you intersect the root geometry, before you intersect geometry in child 2, and therefore this is the right algorithm to do the intersection tests. Which is child 1 versus child 2 is chosen based on viewpoint. Essentially, with respect to the root node of the splitting plane, child 1 is on the same side as the viewpoint, and child 2 is on the other side. So you can think about this in a simple and intuitive way that you first intersect the geometry that lies on the same side of the viewpoint as the same side as the camera. Then you look at the splitting plane, and then you look at geometry behind the splitting plane that lies on the other side of the camera. The nice thing about the BSP tree is that it's built only once, but then you can use it for any viewpoint. And in fact, similarly for regular grids and bounding volume hierarchies, they're not rebuilt if you change your viewpoint. Finally, I just want to say one word about interactive ray tracing. Ray tracing as a technique has historically been slow. In fact, when you build your ray tracers, the speed of the ray tracers is a major challenge, which is one reason I suggested that if you can, you might consider developing in a modern system like optics. However, over the years, the power of ray tracing has increased very dramatically. Initially, it was a viable alternative for complex scenes. The key idea there is because you have ray tracing acceleration structure, the complexity is sublinear with the number of triangles. You do not need to process all the triangles in the scene, which you would need to do if you were running a rasterizer or OpenGL method. Moreover, ray tracing automatically gives you realistic shading effects, and it allows many effects that would be difficult to do in OpenGL, such as soft shadows, reflections, interreflections. But even in the standard weighted ray tracing, we can do reflections, refractions, shadows, which are difficult to do in OpenGL. But in the last 2 years really, and I'd say more broadly in the last 5 to 10 years, graphics hardware and software has progressed at an amazing rate, starting with perhaps NVIDIA's OptiX 5 and OptiX 6 and the RTX graphics chips that came out in 2018, which are now claiming speeds of 1 billion to more than 10 billion rays per second. And this completely changes the game to where you can ray trace complex scenes in video games at real-time frame rates. While most video games are not based purely on ray tracing, today we are increasingly seeing ray tracing based solutions for games, and NVIDIA, which is the biggest maker of these kinds of graphics cards for gaming engines, is pushing the idea of real-time ray tracing in games. Within the production or movie industry, there has already been a shift to physically based rendering, essentially using the methods of these course over the past decade, starting around 2011. And those techniques are already based on ray and path tracing. So the ray tracing revolution has taken perhaps 40 years since the first ray tracing images in 1980, but it is here to stay. And this course will explore the many exciting things you can do with ray and path tracing.